Buenas tardes todos los aquí presentes, buenas tardes los que nos están viendo por videoconferencia, el Colegio de la Frontera Norte, la Universidad de Guadalajara, la Universidad de Yucatán, el CRIM, el INEGI, la Universidad de Córdoba en Argentina y la Universidad de Barcelona, que lo va a ver por el cambio de horario un poco más tarde retransmitido, y también algunos colegas en la Sorbona y en Francia. Esta es la segunda presentación del doctor Courgeau bajo la Cátedra Bourgeois-Pichat, la cuarta que tenemos. Para aquellos que no vieron la primera, esa fue una vista general de cómo se da el tratamiento de grupos a individuos y el nivel análisis multinivel. En esta ocasión yo le pedí al doctor Courgeau que nos hablara. Él es un gran metodólogo francés que ha inventado métodos, que siempre está generando y creando nuevas metodologías demográficas y estadísticas, y en esta ocasión le pedí hoy martes y el jueves que nos platicara de los últimos avances que está realizando metodológicamente, pero que nos hiciera un ejercicio además, o sea que fuera como tipo clase y luego con un ejercicio práctico como para ver la aplicación de la metodología. El título de esta ponencia es la importancia de la inferencia estadística en los estudios de población. Y bueno, yo creo que no necesita más introducción, la mayoría de ustedes estuvieron al día de ayer viéndolo, entonces le paso el micrófono al doctor Courgeau.
Thank you very much, Fatima. You can hear me? No? That's good? Okay. So today we shall treat statistical inference here as a process that allows, as a process that allows a transition from data regarding a set of units or individuals in demography to statements about a new unit or a new individual. Since the inception of demography, and more generally, the social science in the 17th century, their units have consisted of individuals. However, these disciplines have devoted themselves to studying the behavior of large populations of individuals. More recently, however, the multi-level approach has fleshed out this hypothesis and shown the existence of multiple levels. These need to be studied simultaneously and on an equal footing in order to identify their interrelationships. We shall try here to show the problems that this approach poses for statistical inference and attempt to solve some of them. For this purpose, we begin by examining a classical statistical paradox that persists in the multi-level approach. It is the Simpson paradox. I will tell you more about that. Drawing on these examples, we shall also see how we can make predictions using the concept of exchangeability. Maybe you don't know this concept, but it's an important one in Bayesian statistics. It was introduced by Definiti in 1974, as well as other hypotheses on the behavior of the population studied. So let us see for a moment the Simpson paradox. We may usefully begin by revisiting the history of the paradox, customarily referred as Simpson paradox, after the author who analyzed it in detail in 1951. In fact, Cohen and Nagel discussed it as early as 1944, while Chung presented it in 1942, using the interesting notions of favorable, indifferent, or unfavorable events. Chung showed that the three notions led to different conclusions, among them Simpson paradox and the notions of non-transitivity. Lindley and Novick, in an article on the role of exchangeability in statistical inference, revisit the paradox in relation to Fisher's concept of subpopulation and the Bayesian concept of exchangeable units. I shall use these analyses to offer predictions consistent with the data and to spell out the reasons why it is tricky to make prediction without new hypotheses. Let us describe this paradox with a simple example given by Rouanet et al. It's a French statistician, French Bayesian. I don't know if you have heard about him. He wrote a book on Bayesian statistics for the purpose of analyzing the structure effect on this data. We suppose that the result of an exam taken by students in a given town are initially tabulated as in table 1. So you see, you have in these tables boys and girls, passes and fails the exam. For the purpose of this discussion, we are not considering small sample problems. You can, if you wish, multiply the figure shown by the factor such as 100,000. This will not change the problem. So you see that the pass rate for boys, 40%, 36 on 60, is below that of girls, 60%, 36 on 60. Okay. However, as the town has 2 high schools, it's well below. We can tabulate also the number of boys and girls who pass or fail the exam at each high school. So we have it in the next table for the separate high school. This time, the result is, on the face of it, surprising. Boys post higher success rates than girls in every school. So you have 15 on 50 and 1 in 10. So in the first school, the pass rate are 30% for boys versus 10% for girls, 1 on 10. In the second school, 90% for boys versus 70% for girls. In this case, the high school is referred to as a confusion factor when we are studying the effect of gender or success in an exam. To resolve this apparent contradiction between these results, we therefore need to analyze the data more fully. For the time being, we can confine our study to the objectivist or frequentist approach to probabilities. This is justified by the fact that we are observing large population as previously noted. The frequency of an event A, P, I don't have it here, I think. P of A is the ratio of the number of cases favorable to the event into the total number of cases observed. Here I have chosen the logit models, but the other probit complementary log-log yield very similar, if not identical, results. So we are looking for a logit model. The logit model is written as follows with a simple notation from the 3 binary characteristics. R stands for the exam results, 1 for pass, 0 for fail. S is the gender, 1 for girl, 0 for boys. And L is the high school, 0 or 1. We can write the probability that R equal 1 given S, sex, and school is equal to 1 plus, you have a formula there, and put it more in the center. Or again, simplifying the notation to P égale, I would prefer to say the formulas in French, because for me in English it's more difficult. You permit me to do so? P égale probabilité que R soit égal à 1, R égale 1, knowing S and L. So log de P sur 1 moins P is simply equal to A0 plus A1S plus A2L. With the previous data, we estimate these parameters. We have A0 égale moins 0,85, A1 égale moins 0,35 et A3 égale 3,04, which enables us to reconstruct the set of probabilities derived from table 2. So we can write every probability. The first one is the probability that the individual had a success, R equal 1, knowing that is a male and is in high school 0. It's 0.3. The probability that he I had a problem. No? Okay. Probability that you have a result knowing that you have a girl and the school is 0 is equal to 0.1. The probability to have a result 1, a male sex, the second lyceum is 0.9, and probability to have a success, knowing that it's a female and the school is the school 1, is 0.7. Oh, okay. So, for example, for boys, we can, excuse me, we are not. First, let us look at the results now. These results show clearly two effects. First, the gender effect is identical for both high schools. Being a girl reduces the probability by 0.2 points. You compare sex equals 0 to sex equal 1, compared with that of boys in both schools. The gender effect, therefore, seems totally independent of a student's school. Second, the teaching quality effect in each school is very clear. The results for high school 0 are 0.6 below those of high school 1, 0.9 between minus 0.3 and 0.7 minus 0.1. It's always 0.6 below those of high school 1. Regardless of the student gender, for boys and girls is the same. The high school effect, therefore, seems totally independent of gender and to be solely dependent on teaching quality. For all this value, you can compute the probability of the events listed in previous table 1. So table 1, I recall you, is these results in the table 1. So we can write probability the result is success, knowing that the sex is 0. Maybe I don't have it here. No, put it here. No. So is equal to 24 on 60, and similarly for girls, 36 on 60. But because the high school is a confusion factor, these results are of little interest for the combined results obtained in different high schools that can generate Simpson paradox, as it is indeed the case here. So now we will try to make inferences from these results. For forecasting purposes, we shall now use the epistemic approach to probabilities, as the inference here will concern only a single new case. The epistemic probability of an event A, the one that may be experienced by the new individual, knowing that another event B has occurred, here the exam results obtained by the previous student, probability of A knowing B will be the degree of credibility of an event, given that we know of the other circumstances. Before attempting to make this prediction, we must also define exchangeability, a notion introduced by Definity, which will make them possible. So you have it in the projector. Let X and Y be two random variables measured for a certain number of units. For the if units, the variables takes the value great XE and great YE, which are unknown to the researcher. Once they are observed, the variables cease to be random variables and becomes the numbers X, little xe and little ye. A number of units n is said to be exchangeable for x if a joint probability distribution, probability of x1, x2, xn, is invariant under any permutation of the units. So, for example, it's equal to probability of x2, x1, x3, x9, and so on. An additional unit is exchangeable for x if a set of n+1 units is exchangeable as well. A number of units n is said to be exchangeable for x, knowing that great Y is equal to little y, if a joint conditional distribution P de x1, xn, knowing that grand YI is equal to petit yi for every e, is invariant for any permutation of units whatsoever. If so, we can predict that the boy has 3 in 10 chance of passing his exam. So we write no, I think I will have something to say before. Yes. For instance, for the 50 boys of high school 0, may be regarded as exchangeable with regard to the exam, conditionally upon the high school affiliation. No, I'm going too quickly. I have not put everything on the transparency, so I have omitted to give you more examples. So it's after an additional unit is exchangeable for x if the set for n+1 units is exchangeable as well. We have, as an example, we can regard 60 boys of table 1 as exchangeable in regard to passing the exam. This is a personal opinion, which, as we have seen, does not resist scrutiny, for success also depends on the high school. That is the example I give for the first thing. For the second phrase, a number of units is said to be exchangeable for x, knowing that y is equal to, great Y is equal to little y. I give an example. For instance, the 50 boys of high school 0 may be regarded as exchangeable with regard to the exam, conditionally upon the high school affiliation. Again, this is a personal opinion, which, as we have seen, is more robust than the preceding one. We can thus show if n is a large number, then the epistemic probability of event R occurring in the n plus 1 case is simply the frequency with which the event has occurred in the previous n cases. A rigorous proof of these results, despite its fairly intuitive character, actually requires definitive theorem on the structure of exchangeable sequences. We will not give here a demonstration of this theorem because it's too, too mathematical. We can thus write the result more simply as little p of R is equal great P of R, where little p of R is the epistemic probability of the event for the n plus 1 individual, and great P of R is the estimated frequency for the preceding n individuals. So you have a new individual, you have a frequency you have calculated for the n previous individuals, and you say that the probability, the epistemic probability of a new individual for which you don't have the result is equal to the probability of the whole population you have seen before. Likewise, if great X is conditionally exchangeable given great Y, we can state that P de A given great Y is equal to little y is equal to P de A, probability, the frequency P de A, knowing that great Y is equal to little y. Where, for example, event A is a boy's success in the exam and Y the high school. To predict a new student's chance of passing a later exam, we need to make assumptions on the exchangeability of certain characteristics. For example, if we want to predict the probability for a new male student at high school 0, we can rather easily formulate the hypothesis that all boys who are students at high school 0 are exchangeable with him with respect to the probability of passing the exam, and that the new student is also exchangeable with them. If so, we can predict that the boy has 3 in 10 chance of passing his exam. That is the formula 1. P de R results to have a result positive, knowing that it's a boy and he is in lyceum in school 0. It's equal to the probability of the other boys in the same school to have this result, that is 0.3. While a girl will have 1 chance in 10. Another example. If we try to predict a new student's probability of success without knowing the high school, but knowing the student gender, for example, male, i.e. S equals 0, we can write probability that the result is positive, knowing that sex is equal to 0. You have a formula that is a little more complex than the previous one, because you have to consider the probability that is coming from lyceum 0 and the probability that is coming from lyceum 1. I have... oh, yes, but you... okay, but I will put it... okay, but I have to put my glasses because... yes. Oh, yes, maybe you... Yes. So, the probability that is the lyceum is 0 and the sex is a male, and secondly, probability that Lyceum is 1 and the sex is 0. It's always a male because we are working on males. But once we have selected a boy, we do not know the epistemic probability of selecting high school 0 or 1. Unlike what we observed in the initial sample, we can see, therefore, that exchangeability for the high school with a given gender is no more firmly demonstrated for this new student than it was for the 60 others. However, as we have seen, the high school effect was mainly due to teaching quality regardless of student gender. We can consider the newly selected student gender and his or her high school are independent here. We can thus assume that the new individual selected is exchangeable by high school with the rest of the population, where the probability of choosing a high school is equal to 60 on 120, that is 0.5. You have it here? Okay. Okay, that's nice. And you have a result, final result, that this probability is equal to 0.6. We can thus see that the new student will be more likely to pass his end-of-school exam than a girl for whom the probability will be 0.4. This result shows that the use of table 1, so the previous table 1 I have shown you at the beginning of is inadvisable for predicting probabilities here, for it yields an opposite result due to the non-exchangeability of observations. So I'm going back. Oh. Okay. Of course, the forecast is valid only under the hypothesis formulated here, i.e. that the high school effect is due to teaching quality, a hypothesis that needs further verification. We shall see how to do this by observing a larger number of high schools. So we are coming now to a multi-level model. Let us now see how to generalize the preceding results to a large number of high schools, N. One solution is to perform separate logic analysis on each high school, E, with gender as the only predictive variable. That is the first formula you have. Yes, yes, it's this one, yes. Just, no, this one, yes, that's good, yes. Probability, yes. Mm-hmm. Ah, yes, okay. Oh, yes, you see. How can I? Yes, I've seen it. So it's equal to the formula given here. Some schools may have very small enrollment, and the standard error of estimate of the parameters A0E and A1E may be very large, making the results non-interpretable. If we want a more general result, valid for a larger population of high schools, all the French high school, for example, we may consider that our choice of high schools is designed to yield more general information on all French high schools. Just as we pick a sample of individuals to deduce estimates for the total population, we can draw a sample of high schools to deduce information on all high schools in France, for example, but in Mexico, if you prefer. As earlier, we use the objectivist or frequentist approach to probability. So we can view parameters A0i and A1i as random variables that we can write as A0i equal A0 plus U0i, and A1i equal A1 plus U1i, where U0i and U1i are zero mean random variables with variances equal to variance U0i equal sigma 2 de U0, variance U1i equal sigma 2 de U1, and covariance U1i, excuse me, is equal to sigma U01. So the model can be written like the one given below. A method exists for estimating the model's parameters and variance-covariance matrix, as well as the U0G and U1I values for each high school. We will see them on Thursday during the presentation of multi-level analysis. I will not speak about this today. So we will now give an example, like for the first case, that extend this again. Oh, it's gone. That extend the one studied earlier. But this time we will take girls know the favored gender. This is better for French data. I don't know for Mexican if it's better. Do you have better results for girls than for boys in Mexico too? Yes, that's true. Thank you. So I will take an example, because the first example was the example that Juane treated. So I take it as he treated it. But I thought that for being more realistic, it's better to think that girls are the more favorable gender for exams. We take 10 high schools in which we initially obtain the total result listed in table 3. For all 10 schools, the girls' pass rate is more than 10 percentage points lower than that of boys at 34.25 versus 45.75. So you see, we have again a Simpson paradox. For all the school, you have an inverse result that you will see for each school. So I will give you now the results for each school. So if for each high school you have these results, and I will give you a little later, but I will give you here the results. So you see that for boys and for girls, the results for boys are always lower than for girls, for each school. But for the total of schools, you have a better results for boys than for girls. I will come back to the... So this is, again, the Simpson paradox that continues to apply to these schools. Let us now perform a multi-level analysis on the high schools with gender as the predictive variable. Our first observation is that the introduction of gender variable into the random variables, you see the random variables are here, gives a zero variance. So we shall therefore eliminate it for the random parameter in later calculation, and we obtain the results shown in table 5. So you have 3 models. I will take them each after the other. Model 1, so that's model 1, clearly shows that boys have a lower pass rate than girls, 26.3 87% versus 41.42%, regardless of their high school. By contrast, we find a random factor. It's okay. It's not, yes, okay. Well, so you have a random factor at high school level, which shows different results for each high school. We can calculate the estimators of these random parameters, U0G, for each high school, and compare the estimated pass rate with the actual ones. So that's the table I showed you previously. Here you have the estimated pass rates and the actual pass rates I showed you previously. And you see that the estimation is quite good. 17%, 20% for the girls, against 15% and 20% for the girls for high school 1, and for high school 10, 59.5% against 64% for girls, and for actual pass rate is 60% against 65%. So this table 6 show a comparison that is entirely satisfactory. The girls' pass rate exceeding that the boy rate, roughly 5 points in each high school. So we will come back to the previous model. In model 2, we had the estimate random for a logit model that is usually equal to 1. We let it free now. We let it vary. And we see that we have an estimate of 0.999, so that's very near from 1. So the hypothesis that the binomial model is applied to the logit model is applied to this data is a very good one. And the results are quite similar to the previous one. So you see that nothing is changed from this discarding of a binomial variance condition at individual level. So in the remainder of our analysis, we can therefore regard model 1 as being fully validated. Model 3 now includes the contextual variable, the proportion of boys in each high school. It perfectly explains the random effect at the high school level, the variance being 0. You see, becomes 0. A simple logit model, therefore, suffices to explain all the observed behavior. We obtain the following pass rate estimation by high school and gender. So we have it as table 7. You see that the results are very near from those we have from the model 1. And the estimates are very accurate. However, although the pass rate estimated by model 1 and model 3 are very close to the observed value, the hypotheses underlying the estimations are actually very different. Let us examine them in greater detail. In model 1, a purely multi-level model, the underlying hypothesis is that the pass rates are determined by the high school and its teaching staff, for it includes no contextual variables that enables us to take account of students' specific characteristics. The random parameter at the high school level is large and substantiates the preceding argument. So that's, let us come back to the model 1. There. So that's for the model 1. Model 3, a contextual multi-level model, comprises a contextual variable specific to each high school, the percentage of male students. Here the percentage plays an essential role, single-handedly enabling us to distinguish between high schools. By contrast, the random parameter for the high school fails to 0, as we have seen. This shows that the differences are now totally explained by the proportion of the two genders and not by the teaching staff, as the previous analysis appeared to indicate. Of course, Model 3 is somewhat artificial and yields these extreme results. In actual cases, the solution is less categorical, but it does lead to very similar conclusions. One example concerns migration by Norwegian farmers compared with other occupations, which I will examine in detail on Thursday's session. An initial pure multi-level model enables us to distinguish migration behavior by region of origin. A second contextual multi-level allows us to qualify these results by showing the effect of a percentage of farmers inhabiting each region. The effect sharply reduces the regional random parameter without, however, offsetting it completely like in this example, but it reduces to the half of its value. Other regional characteristics plays also a role, but we were not able to measure them. So we have to let this part of variance unexplained, but we know that it exists. So we will now try to make prediction, and we shall take this new aspect into account. So let us come back to the... We can again make prediction from these results. If we pick a new individual, can we predict his or her success with the aid of the parameters alpha 0, alpha 1, alpha 2, U01, estimated from the population initially observed? As before, this prediction will be an epistemic probability. Let us examine various cases, for we have seen that the hypothesis will change significantly depending on whether we perform a pure multi-level analysis or a contextual multi-level analysis, as I've said you previously. We begin with the results of a pure multi-level analysis. As noted earlier in different terms, the exchangeability test will concern the student's success in the exam, taking high school and gender as given, the effect of the two factors being independent. First, let us observe a new student of a given gender attending a given high school. Accordingly, if this is a new male student, for example, taking the same type of exam in high school number 7, we can estimate his pass rate as before using model 1 in table 5 and the estimates of table 6. So we can write that his probability to have a success at his exam will be equal to 0.448%. With the same model, the result for a girl attending the same high school will be 49.6%. So you see, you will have to go to the results of high school 7 to have these results. 44.8 and 49.6, you see them? Okay. If we disregard the high school, we can write again the formula, the long formula, but it will be longer than previously because we have 10 schools. So the probability that the result is 1, knowing the sex of the individual is a male, is the probability knowing his sex is a male, but is in first lyceum, multiplied by the probability to be in the first lyceum, knowing that he is of sex 0, and so on, until the last one. And this yields probability R égale 1, X égale 0, is equal of excuse me, I'm going too far, too quickly. We know the probability of success for boy in each high school from the percentage observed, but we do not know the epistemic probability for the high school by gender. So we cannot estimate this formula simply. For model 1, we can assume, as in the previous two school example, that all these probabilities are identical and equal to 1 in 10 in this case. In the previous case, it was 1 in 2. For the high school effect seems to be independent of student gender here. We thus obtain this result, probability of R equal 1 is equal to 0.369 and 0.4. In other words, a higher probability of success for a new girl than for a new boy. These results contradicts the use of table 3 for all schools combined. Again, we have not to use the table 3 which gives you the results for the whole school. You have to use the results for each school to estimate, even when you don't know the school in which the individual is. Lastly, let's see. If instead the new student is enrolled in an out-of-sample as high school, we must reason slightly differently. As the high school is out of sample, we cannot estimate its random parameter. We therefore need to posit it as equal to the mean for observed high school, i.e. 0. This yield probability R égale 1, this is the probability that we estimate, with the probability equal to the mean for observed high school. We can see that this result is very close to the one obtained when we disregard the high school despite its being in the sample. Let us turn to the results obtained with a contextual multi-level analysis. The exchangeability test now concerns the student's success and the high school effect measured by its percentage of boys given the new standard student gender. We return to the first case in the previous analysis, i.e., a new male student taking the same kind of exam in high school number 7. If we have no information on the percentage of boys taking the test, we can assume the percentage is unchanged. That is always the same percentage. For the previous example, and model 3 of table 5 gives us this probability equal to 0.445. For girls attending the same high school, the figure is 0.5, a result very close to the one given by model 1. However, if the percentage of boys in the high school has changed from this exam, which is information that could be known in advance, model 3 will supply another estimate of the pass rate. Indeed, if the percentage of boys fall, for example, so we have to come back to the table, the percentage of boys falls from 65. No, it's not. It's the previous. No, excuse me. 65 to 50, 55%, the expected pass rate will drop to 22%. 29.2% for the relevant characteristic is now the percentage in table 7, excuse me, of boys in the high school and not the high school itself, whereas model 1 will still give 44.8%. In this case, the prediction generated by the two models may diverge sharply. If we now disregard the student high school, we can continue to write the same formula as before, but the hypothesis posited for model 1 does not apply to model 2, for we see that it is the percentage of boys in the high school that introduces the differences in exam outcome. Absent new information on the percentages of boys for this new exam, the most relevant percentage will thus be observed in the previous test. This will lead to the following probability of success: 0.45% for a new boy and 0.34% for a new girl. In other words, these results correspond to that of a combined high school in table 3 and contradicts the results supplied by model 1. I will not give you the detail because I think it's not useful. If we know the new percentage of boys in each high school for the new test, we must apply them to determine a new boy's probability of success. If the percentage of boys are equal to those of girls in all high schools for the new test, then the result will be close to that obtained by model 1. No problem. Indeed, using the results from table 7, we find probability equals 0.37 for boys against 0.38 in model 1, and 49 for girls against 42% in model 1 as well. On the other hand, each possible distribution of boys and girls will now yield a different results. Lastly, let's examine the case of an out-of-sample high school. If we assume that its percentage of boys is known, we can produce a more satisfactory estimate than with a simple multi-level analysis. For example, if the percentage of boys is 70, then the new boy's predicted probability of success will be 0.429, a value interpolated between the results for high school with male enrollments of 65 and 75%. However, if a percentage is unknown at the time of estimation, we shall have to make do with the value 0.366, a figure close to the one we would obtain with a simple multi-level model. I'm sorry, but this is too much complicated to show you with these tables, and I have discussed these examples in detail to show how the results differ according to our choice of the most relevant exchangeability test. But here it is obvious that we must choose model 3 as the most suitable, for it uses all the information contained in the data tables 3 and 4. To conclude, this paper has enabled us to show how Simpson paradox could be properly resolved by using an appropriate multi-level model, and how the use of a concept of exchangeability allowed a statistical inference from the observation of a sample. However, the link between the initial sample and the new individual for whom we perform the inference must be formulated with great care if we want to make an accurate prediction. The links requires underlying hypotheses for data in order to set the precise condition for exchangeability and arrive at the final inference. For instance, with the first pure multi-level model, we assumed that exchangeability concerned the results determined by high school and gender, whereas in the second contextual multi-level model, exchangeability concerned the results and the high school conditional upon only the student gender. The later analysis was confined to two subpopulations, boys and girls. a student enrollment in a particular high school is taken into account only via the percentages of boys in the school, not via the quality of the teaching staff. Naturally, there are other possible approaches for dealing with this inference problem. For example, we can replace the concept of exchangeability and conditional exchangeability by those of population and subpopulation used by Fisher. But the fact that exchangeability explicitly refers to random variables, whereas the concept of population cannot do so, diminishes the values of the Fisher approach. It is very hard to specify how an individual can be viewed as a member of a given population, whereas the exchangeability criterion, which applies to units, to individuals, offers a clearer means of connecting individuals. That is why we have not elaborated on the frequentist approach and have preferred a Bayesian approach to inference here. We have also assumed that we were working on a large sample that would enable us to estimate the probability used to achieve their inference from their frequency. However, working on a small sample will generate complexities, for we shall need Bayesian methods to estimate the probability of the event studied. This calls for a discussion on the exchangeability of a small number of individuals that we shall not go into here. Arguably, however, such a discussion will provide very little information on the inference to be performed, making the issues fairly irrelevant. In conclusion, we can say that the data do not supply sufficient information to perfect a correct inference. That requires other information as well drawn either from the analysis performed using this data or from the researcher's practical experience of the subject. Thank you very much. So, okay, no problem. So I can go to the examples. So that's the use of MLWin. MLWin is a program, is a program proposed by Harvey Goldstein, which is an Englishman which has made very good work on multi-level analysis. And I asked to Fatima if you have it here, but she told me that you don't have it. So I have to make some figures taken from my computer. So that's the example I treat in the paper I presented you before. This paper will be published in the review Mathematical and Social Sciences. It's in the last issue of this year. It's not yet published, but it will soon appear. And these are the tables you have from MLWin. So I will give you some information about these tables. So that is the first table of names. So you have the school, the sex, you have the school, the sex, the exam, the student, the boys, and so on, and some constants you have to introduce to make your estimation. Here are the number of cases you have in each for each variable, and it's 45,000 people. Missing information, you have no missing information. The sample is complete. Here you have the minimum and the maximum of each variable. So you have to go from school 1 to school 10. For sex is male and female. For exam is the result of the exam. 0 he fails, 1 he had his exam. The student, that is the number of students. So you have the number of the school, but in each school you have students numbered going from 1 to 400. So you have here a simple example. You have 10 schools with 400 children that give you 4,000 people. The percentage of boys afterwards, you have 0.05 to 0.95. So the schools are very, as you have seen in the tables, different each others. And these are only constants that are useful to estimation of a model, but they are not to be presented here. So, okay, but it's not the following one. No, it's not the following one. So we have to go. Yes, okay. I will verify. Yes, it's okay. So, this is a second table you can get from your data. It's the table of data. So you have, for different variables, here the school, here the sex of the individual, here the exam, here the student, the result of the exam, here the student, and here the percent of boys in this school. So you are here in school number 1. It's the beginning of a list of 4,000 schools. You have the sex. There are only men in this file, but afterwards you will have females. Exam, the result of the exam, so it's 1 here and 0 after. The number of the students, so you have here the number of the students, that is, and the percent of boys that is in each school. That is the first school with 5% of boys only. So, these are the questions of a model. You have the exam that is binomial with denominator EG, that is the denominator is equal to R1, and PEG is the result you got. Logit PEG is the probability of the individual. No. No. Okay. So you can have different models. You have normal models, binomial models, and so on. So here I put a binomial model. And this is the model that I estimate. So the logit of probability of having the exam is equal to beta 0 multiplied by sex and beta 1g multiplied by constant. And here I introduced a random term, U1G. So you see beta 1G constant. Constant is the variable 1 you have seen before. So it's beta 1 plus U1G. And you have here, for the U1G, it will be a variable of mean 0 and variance P G. This is the variance you have to estimate. This, yes. So that are the results. So you have always the equation, but you can let the model run and have the estimates. So you ask here the estimates, and you see that you have something you have here. Here you can put the name of a variable. So I have not the first variable, but you have the sex and the constant. Here you can have a possibility of nonlinear estimates. That is the case here, but I did not give you this possibility. I will give it to you at the next sessions. And here you can add a new term, and here are the estimates. That is that we have here. So we have the results. 0,191 multiplied by sex, so it's sex 0 or sex 1, and this is the variance of the estimate of the parameter. And you have beta 1G multiplied by cons. Beta 1G is equal to moins 0,538 plus 1G that will depend on the school. And you have the estimate of the variance I gave you before, that is 0,384 with a variance of 0,178. And this is, I estimate the second model. You remember I have put the variance to be not equal to 1. And you see here, you have the estimate 0.999. That is with a variance of 0.22. That's good. Ah, it's okay. Oh, attendez. No, 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 but you have to come back. Yeah. Yes, no. Ah oui, parce que... we'll see if we are following the good... So, that is the next model. So you have always the equation, binomial, and the model logit. So you have here the sex and the percent of boys. So this is the complete model I've estimated, with beta 1G is equal to minus 0.641 plus E1G. And you see that the variance of E1G is 0, as I told you previously. And here I've kept the model with variance estimated, but it's not useful because you will have a variance equal to 1. So what for following? What's occurring there that I don't have? I don't understand. What? But no, no. So, but you don't have all the tables given here? Maybe yes. No. Okay. So you have to turn it, and I will have to tell you something before speaking about that. Okay. Thank you. So. No, thank you. Yes, yes. Okay, thank you. So, here is an example of Bayesian multi-level analysis. I told you that in the example I give you, I made only a frequentist approach. But here, to give you an example of using a Bayesian model with MLWin, I tried to estimate the same parameters than previously, but with Bayesian models. So I will tell you something about these Bayesian models. I will not tell you about this in the next session, so that I will tell you about this now. We can estimate Bayesian models using MCMC, Markov chain Monte Carlo, MC, Markov chain, MC Monte Carlo, and bootstrap models with MLWin software. The MCMC method derives its name from the following notion. To produce acceptable approximation of integrals and other functions that depend on a distribution of interest, it is sufficient to generate a Markov chain for the limit distribution, i.e. the distribution of interest. On the other side, the bootstrap method consists in building a series of samples similar to the observed sample and to use a series to estimate the distribution parameters of interest. We have assumed here that a binomial model was well suited, and as we showed in our non-Bayesian example. This assumption is easily confirmed here in the Bayesian example. For the MCMC option, we use the Metropolis Hastings sampling method, which is applicable to binary data, such as those studied here. The algorithm allows the construction of a generating mechanism to produce Markov chains converging toward the distribution of interest. We have also two alternatives for the a priori distribution. We have a gamma distribution. So you see the MCMC, but I will present you gamma distribution or an uniform distribution as an a priori distribution. We shall use both. The estimation were performed with 20,000 iterations. For the bootstrap option, we have chosen to perform 500 draws in 10 sets. A first test on 100 draws in 5 sets gave us bimodal estimates for the core density of certain parameters. I will show you later the results because I will first give you the main results, and afterwards I will show you the MLWin results you have in the computer. We have used the parametric option, taking the least square estimators our starting point. The non-parametric option yields unstable results as the parameter values increases with the number of iterations. We have not reported the figures here. So, table I8 you have here lists the resulting estimates of a fixed and random parameters with a reminder of a non-Bayesian estimate. So you have here the parameters, fixed, intercept, and gender, and random. That is for the first model. And you have a variance of 1 as it is a binomial model. So that is the non-Bayesian result we get. And these are the Bayesian results we get with a gamma prior or a uniform prior. You see that the results are very near. But for the random variable, you have here an important increase, mainly of the variance of the estimate, so that it's no more significant, while in the non-Bayesian model, it was entirely significant. So you see, you have some problems here when using non-Bayesian estimates. For the bootstrap methods, yes. So I will tell you, yes, okay. A higher variance of this random parameter, not significantly different from 0, particularly when the a priori distribution is uniform. The use of a parametric bootstrap is here. By contrast, produced an estimate of a random parameter that is very close to the one obtained with a non-Bayesian model and very significant. So you see that the bootstrap method is very near to the non-Bayesian one, and mainly for the random variable that is always clearly significant. So that's a problem with such estimates. You see that the random variable become not significant. And you have a core density, so I will show you, but I will not go into detail here about this. And values accuracy diagnostic for the estimators are given. Raft, Lewis, Quantils, and Book-Draper. They offer no new information with respect to the non-Bayesian model. When we introduce the percentage of boys, we can no longer estimate any MCMC model. So you see the MCMC model will not be usable when you introduce the percentage of boys. This may be due to the fact that the sample we have constructed no longer comprises random parameters. To avoid this, we should design a much looser sample, but in contrast, the sample allows us to estimate a bootstrap model that is given in table 9. And we can see now that from the non-Bayesian I gave you here and the bootstrap parametric model, the results are very near each other. So as we have a great number of people, the results from the bootstrap model are very near from the non-Bayesian one. But for the MCMC model, there are problems, and I asked to Harvey Goldstein if he can tell me why these problems occur, and he told me, I think it's because we don't have random parameter in the second sample, so that we cannot estimate the model. We can conclude from this examination that the Bayesian multi-level model does not contribute to truly novel results in the present case, where the size of the population observed is large. the prediction identical to those obtained with a non-Bayesian model. So as a reference, you can go to the book by William Brown on MCMC estimation in MLWin. That is given with the MLWin program. You will find there details on the diagnostic that I will not develop here, but only show you that they exist. And the result I will show you are not exactly the same as I had in my paper, because as they are sampling methods, the results are always different. So you have to consider the result and the variance of the results to see the effect you have. But you will see that the results are not the same as that I gave you here. So we will go to the next one. So I think we will have to re-put the master. Okay, that's, you have not, voila, okay. So, here you have estimation control. You have EGLS and REGLS. These are some methods of iteration that are not of importance for us. But here you have MC method, and here bootstrap methods. So here I have clicked on the MC method. We have a burn-in length of 500 chains and a monitoring chain length of 5,000 of length 5,000. No. It's, oh yes, so that's the next model. Just to give you, no, 5,000 is the same, is the same. So that is the result. Yes, so it's a MC result. But I think I did not put. No, that's okay. So you have here for the sex, you remember that we had something quite different previously. We have 0.193 here, but here the effect of sect is 0.82. So you have the effect of a constant with the variance of the term, and that is the random term that is equal to 0.528 with a variance of 0.326. But it's the same. So these are not of very great interest. That are the results of the different parameters. For each iteration, you see that you have something that is, I just give you an example. And this is always the same. Okay. This is always MCMC, but with a monitoring chain length of 20,000. Twice. Okay. And I get these results. So, yes, I have an estimation of type PQL. It's with a second order linearization, but I think this is internal to the models. You have to try a first order linearization and then a second order linearization. And you have these results for the sex and for the variance. And here the variance is equal to 1, and here 0.528. So these are always the parameters with the estimates. And here you have for each parameter, so that's for the parameter beta 2, I think the most interesting is the value, the mean value of a parameter you have here, and the estimate of its curve. You see it's a nice curve, it's quite normal one, that's good. And you have different tests that I will not go there, but you have here some quartiles between which you have a posterior means, that is the estimates you get, with a standard deviation of 0.2. And here you have different diagnostics that I will not go into. That is for the parameter, it's beta, I think, I don't have it, I think it's beta 2. We don't have summary statistics. I don't unfortunately, I have not taken them here. And this is for the variance, which is 0.528 with a standard deviation of 0.36. And you have here it cannot go under 0 as it is a variance. So you have a curious distribution that is not quite a normal one in this case. So now that is a bootstrap method. You have here indicated that it's a bootstrap method with 100 replicate set size and OLS, ordinary least squares, and different displays. That is the results you get. So as I told you, the results are not the same as those I give in the table. You have here the beta 1G with a variance also equal to 0.995. 7, excuse me. And these are the results of the estimation that are not very interesting. So you have for each parameter, every MCMs, every bootstrap you make, you have an estimate that change each time. And this is, so here you have for the parameter beta 0, it's not very good. You see that its variance is very large, and you have two maximums, and the posterior mean you have 0.186 will be here. It would not be at the maximum, it's near here. You see you have two maximums, and it is not a very good estimate. That is for the sigma, the variance parameter. This is better. So you see you have something that is quite normal here, and the value, mean value 0.441 with a standard deviation. And this is the model always it's always a MCMC, so I don't think it's useful to have it. This is the bootstrap model that gives you the final model with the sex variable, the constant variable, which has a U1G that is near 0 this time, with a variance of 0.9, so it's no more significant, and the effect is mainly explained by the percent of voice you have here with this coefficient. But it's the end, I think. I think I will show you all the examples. So if you have some questions.